Hey, AP Statistics, welcome to Chapter 2. We're going to continue our topics in data analysis in this chapter. So this is still kind of that same idea of we're making sure we understand how we can analyze and describe data. So specifically in this section 2.1, we're going to look at describing location within a distribution for parts of data. The goals for this section are, by the end of the section, you'll be able to find and interpret percentile of an individual value within a distribution of data. We're going to be able to estimate percentiles and individual values using a cumulative relative frequency graph. A new type of graph for basically just seeing percentile. We'll find and interpret the standardized score, the z-scores, z-score of an individual value within a distribution of data, and describe the effect of adding, subtracting, multiplying by, or dividing by a constant on the shape center and variability of a distribution of data. So first things first, percentiles. So this is a way that we measure the location of a data value within a distribution. Basically what percent of the values are less than it. So what percentiles, the percent of values in a distribution that are less than a particular individual. You guys have probably dealt with percentiles before. So here we get kind of a weird looking stem and leaf plot, but Jenny's got a score of an 86 on her test. How did she perform relative to the rest of the class? So we can look up her percentile, her relative position, measuring that location within the distribution. So here's her value, this 86. So if we count up all the values below it, they're highlighted in purple. We count up each of those. Works out that there are, if you kind of pause and count there are 21 values below her score. So her value is greater than 21 of the 25 observations. And we divide 20 by 25, convert it to a percent. Or 84% of the values are below her. Then her percentile is the 84th percentile. So it's actually kind of interesting. We don't use the percent symbol here anymore. We change it to the 84th, and then it's percentile in that distribution of test scores. All right, so we can take data and we can kind of convert each data value into percentiles and graph it, and what we end up with is a cumulative relative frequency graph. These also have a fancy name. They're called ogives, O-G-I-V-E. You don't need to know that term, but a cumulative relative frequency graph plots points corresponding to the cumulative relative frequency, which is just a fancy word for percentiles. Cumulative up to that point. The relative frequency up to that is a percent, so it's percent up to that point. And so we look at those, and we start at 0% for the smallest value. The cumulative relative frequency up to that point is 0% of the data, and we end up at 100% of the data. And we kind of see how we get through the data as we go through it. So let's take a look at an example with some frequencies. So we've got the age of the first 44 presidents when they were inaugurated. We've got some age ranges and a frequency table there for them. And so that's frequency. The next thing we can do is we can convert those you can actually do this in either order, but we're going to convert those to relative frequencies. So that's percent. So out of the 44, we can convert those to percent. And so now we're at relative frequency. And then we can take that one more step and make that cumulative frequency, I'll back up, sorry. We could have done this either way. We can do relative frequency, turn them into percents, and then we can go convert to cumulative relative frequency by adding up those percents. So 4.5 plus 15.9 would get us to 20.5, plus another 29.5 gets us to that point. And so that means that, for instance, 50 to 54, 50% of the data values are at or below that interval. And then we kind of keep going all the way up until we get to 100%. That's one way to do it, is just to add up your relative frequencies as you go. The other way we could have done this is to actually go cumulative first and add 2, and then add 7 more. We get up to 9, cumulative 9 or less than or equal to this interval, 22 or less than or equal to this interval, 34 or less than or equal to that interval, and then convert those to relative frequencies. So you can either go relative first and then go cumulative with it, or you could go cumulative first and then make it relative by dividing each of those by 44. And so that's how we can get to those. And so then if we plot a graph of this, starting at 0% at the left, so there's 0% less than or equal to 40, and then by the time we get to 44, there's 4.5%. If we graph that, we get this cumulative relative frequency graph. and we have their age at inauguration, and so we can see this kind of curve here. So 100% of the individuals were age, this looks like about 70, but it's 69 or less. And so it's basically less than or equal to that. At this point here, 60 or less, it's really 59 if we look over here real carefully, but 60 or less is about 78%, 77.3%. And so you can see the percent below that particular value or that score. Nobody was below 40 in this data set. So we can measure that, and that's kind of giving us our percentile. Like what is, we can estimate a quick percentile. How about somebody who's age 65? What's their percentile? Well, we kind of look up here, and they're in about the 80, 90, 94th percentile. I don't know, 93rd percentile looks like, depending on whether you go 64 or 65. So you can kind of estimate percentile for that. Or how old was somebody to be in the top 20%? Well, then we can look here. Top 20% means there's 80% below them. And so the top 20%, we follow this line across and see, okay, it looks like they may be a little over 60, 60, 61. We can kind of estimate it from that. Bottom 10% of ages, we could look, straight across here. Bottom 10% hit the line and then come down. Looks like maybe 47. That's an estimate. We don't know for sure because it's kind of falling in that interval, but we can get an estimate of that bottom 10%, that 10th percentile score, or age in this case, would be like 47 or 48 or something like that. All right, so that's one way of measuring relative position and then plotting it in a cumulative relative frequency graph. Another way we have for measuring relative position is, and this is kind of more similar to like the first one, percentile, is kind of more similar to how we think about with median and interquartile range and so on. It's all kind of about relative position within the data, just how much is below you, how much is above you. This is more like what we would use with a mean or standard deviation. We call it a z-score. So it tells us how many standard deviations from the mean the observation is, and in it we also have the direction based on the sign. So here's a formula we have for z-score, also known as a standardized score. So, and this is nice because we can compare different distributions with standardized scores if they come from different groups with different means and standard deviations. Well, if we standardize and put it into z-scores, we can kind of make a comparison between these. We standardize to get it all in like the same standard. In this case, it's the number of standard deviations from the mean, and you can compare different groups with this. So basically, you take the value that you're interested in, find the different or kind of a difference, subtract the mean. And so if your value is above the mean, this number will be positive. If your value is below the mean, this number will be negative. And then divide by the standard deviation to figure out how many standard deviations you are above or below. So if the value is exactly one standard deviation below the mean, so you'll subtract this and you'll end up with the standard deviation divided by standard deviation. You'll end up with a z-score of 1. If it's below the mean, you'll end up with a negative z-score because you'll be some distance below the mean. Maybe you're 2 standard deviations below the mean. So you end up with negative 2 standard deviations up here. Divide by that standard deviation turns into negative 2 for that z-score. So an example of calculating one of those, Jenny earned a score of 86 on her test. It's the same data we were thinking about before. The class mean is an 80 and the standard deviation is a 6.07. Find and interpret her standardized score. So we would take 86 minus the 80 divided by the standard deviation 6.07, and we get, so that ends up being about 6 divided by a little more than 6. We end up just under 1. Just under 1 standard deviation above the mean. And so that's what we can say there. Jenny's test score is 0.99 standard deviations above the class mean of 80. All right, caution with this, do not interpret a z-score as a distance away from the mean. It's always above or below with the sign. If it's a positive z-score, it's above the mean. If it's a negative z-score, it is below the mean. All right.